aromaticity is not only applied to neutral compounds, it can also apply to ions, and of course ions can either be negatively charged or positively charged. Let's take cyclopropene, and then let's see what ions can be made from cyclopropene, and then we can examine them for their aromaticity, whether they are aromatic or not aromatic, of course, following the four aromaticity criteria. Let's take then, as we agreed, cyclopropene. This is cyclopropene, of course. It's a three-membered ring where there is a double bond between two carbon atoms. Now, the ions that can be made from this is either a positively charged ion or a negatively charged ion, or even a radical. So if you like, charged species, if you like, in general, okay, something like this is possible. This is another, basically the carbanion. This is another possibility, and of course the radical, where the carbon atom has a single electron. This is a radical, this is a carbocation, if you like, and this is a carbanion. Now, if you look at these ions, you would see that they are cyclic, so there's no problem with that. They are cyclic. The question is, are they conjugated? Well, if there is a carbanion here, then there is a p orbital, because these two electrons must be situated, if you like, in a p orbital. Remember, the shape of a p orbital is like that. So there is a p orbital here, a p orbital here, and a p orbital here. So there is conjugation here. Now, if you look at this positively charged carbon, there has to be an empty p orbital. So a p orbital like that one, but it's empty. So still conjugation is possible here, because there is a p orbital here. Of course, there is a p orbital here, which are occupied. There is a p orbital here, but vacant, if you like, or empty. But conjugation is still possible, because there can be an overlap, if you like, between a p orbital on this carbon and the empty p orbital on that carbon. If you look at this radical, there is also a p orbital here, so there is no problem with that too. Okay, but the number of pi electrons, if you look here, 1, 2, 3, 4, so there are 4 pi electrons here. 2 electrons come from the double bond and 2 electrons from that lone pair. If you look at this carbocation, there are only 2 pi electrons in this case, 2, and here, of course, there are 3 pi electrons. So are they cyclic, these structures? Yes, they are cyclic. Are they conjugated? Yes, they are conjugated, so there is no problem with that. They are cyclic. They are conjugated. Are they planar? They are planar. Do they obey the Huckel rule? That's really the important question. And remember the Huckel rule. If n is 0, the number of pi electrons is 2. So if you like, 2 entitles, or if the number of pi electrons in a specific molecule or specific ion is 2, then that can be aromatic, because that's in accordance with the 4n plus 2 rule of the Huckel rule. That's if n equal to 0. If n equal to 1, it's 6. So 2 is 6, and then 10, and so on. Now, if you look at these numbers, this is 4. So 4 is actually between 2 and 6. So this cannot be aromatic. Therefore, that's because this is not 4n plus 2. This is not 4n plus 2. And therefore, this carbanion is anti-aromatic. That's because it has 4 pi electrons, and that's not 4n plus 2. Remember, n is an integer, a mathematical integer, which has nothing to do with the number of pi electrons. There are 4 pi electrons here, but that's not 4n plus 2. So this is 4n plus 2 numbers, if you like. Now, this ion, or this carbocation, has 2 pi electrons. 2 pi electrons. Is it one of these? Yes. So this is good. Now, therefore, this carbocation is aromatic. That's because this number is 4n plus 2. It's 4n plus 2, 2 pi electrons, and that's in accordance with the Huckel rule, the 4n plus 2. 3 pi electrons. In this case, of course, there's It's not one of these numbers. So this cannot be 4n plus 2, and therefore this radical is anti aromatic. So therefore cyclopropene, which itself is not aromatic, by the way, or anti-aromatic, that's because there is sp3 hybridized carbon, as we saw before. Itself is not aromatic, but if we make a carbocation from it, the corresponding carbocation, then this corresponding carbocation, which is shown here, is aromatic. That's because it is cyclic, it is conjugated, it is flat, and the number of pi electrons, which is 2, that fulfills the 4n plus 2. So this carbocation has satisfied all aromaticity requirements. That's why it is aromatic, whereas the other, this carbanion and this radical has not. That's because the number of pi electrons in them is not in accordance with the 4n plus 2 or the Huckel rule. That's why these two ions, if you like, this carbanion and the radical, are not aromatic or anti-aromatic, whereas the carbocation is.